Okay, welcome everybody to today's UCLA acid-base conference. What I'm going to be talking about today are the basics of acid-base chemistry, and then we'll sort of ascend the ladder and eventually get to how to make an acid-base diagnosis. So just some history about clinical acid-base analysis. It was really Schwartz and Rellman in the 1960s who developed the approach that we now use today. And it's called the bicarbonate-centric approach because it relies on focusing on what the bicarb change in the bicarbonate concentration is. There were other approaches that you might have come across. You've heard of base excess. That was also developed in the 1960s by Astrup and Sigurd Andersen. And then in the 1980s, an entirely different approach was developed by Stewart, and it's called the strong ion approach. But today I'm going to be focusing on the approach that we use at UCLA and in most places in the United States called the bicarbonate-centric approach that came from Schwartz and Rellman at Harvard. So let's talk about the most prevalent buffer system in the body and in all mammals. It's the bicarbonate. It's called the bicarbonate buffer system, and it's actually composed of four entities. It's no different than when you bubble water with carbon dioxide, you end up with four compounds in the solution. Okay, so the first is called CO2, and that refers to dissolved carbon dioxide gas. The second entity, H2CO3, is called carbonic acid. The third is bicarbonate, and the fourth is carbonate. So it's very important to realize that in any aqueous solution bubble with carbon dioxide, you have these four species that I'll show in a minute are at equilibrium with each other. And the same is true in our blood, any fluid in our body, inside our cells, our cerebral spinal fluid, our gall fluid in our gallbladder, any fluid in the body that it has a bicarbonate buffer in it has these four substances. We tend to focus clinically on the bicarbonate only and ignore these. So the buffer system really it's called a system because there's more than one carbonated species and they're all at equilibrium with each other. At equilibrium means that they break down and form at rates that are equal, and so there's no change in the concentration. That's what equilibrium means. So, for instance, if I bubble water with carbon dioxide to make seltzer, it'll combine with water to make carbonic acid, and that can break down to a proton and bicarbonate. And the bicarbonate further can break down to an additional proton and carbonate. And at equilibrium, all these things are unchanging and they have certain steady state concentrations. So the most prevalent by far is bicarbonate. It's around 24 millimolar. The next biggest is dissolved carbon dioxide, which is 1.2 millimolar. This, as I'll show, can be calculated by taking 0.03, which is called the solubility coefficient of carbon dioxide, and you multiply that by the partial pressure of carbon dioxide. Let's say it's 40 millimeters of mercury in the units we use clinically. We don't use Pascal or other units. We could, but using the units we use typically in medicine, with a PCO2 of 40 millimeters of mercury, you multiply that by 0.03 and you get 1.2 millimolar. The other two, the carbonic acid and the carbonate, are in the micromolar range. So we can essentially ignore those. The major two are the bicarbonate concentration and the dissolved carbon dioxide concentration. Now, when we send down a metabolic panel, we get something back called this. Unfortunately, many people call it the CO2. And as renal fellows, if you could stop using that word because it's not chemically correct, it should be called the total CO2 because the measurement includes all four species. So it's the total content of carbonate of compounds in the bicarbonate buffer system that have a carbon atom attached to them. So it includes bicarbonate, carbonate, carbonic acid, and dissolved CO2. Now, people erroneously call this CO2. You shouldn't. It should be called the total CO2. And the other error people make is that they call this bicarbonate, and it's not bicarbonate. In fact, there's no way to measure bicarbonate clinically. We can measure the total concentration of all these things, most of which is bicarbonate, as I mentioned, but it is not equal to bicarbonate because it also, at least quantitatively, includes the dissolved carbon dioxide, which is also in the millimolar range. And as you develop a respiratory acidosis, this can go up and up and up, and the bicarbonate stays the same. So you can have an increase in your total CO2 that has nothing to do with the bicarbonate increasing. So from now on, after this lecture, if you could please not call the entity that you measure on the metabolic panel CO2, call it the total CO2, and for sure don't call it bicarbonate. Okay, very important teaching lesson from this slide. So when you get this back, it's around 25 millimolar. The bicarbonate's around 24. These two are in the micromolar range, so you can ignore those. And as I mentioned, at a PCO2 of 40, the dissolved CO2 is around 1.2. The dissolved carbon dioxide gas is around 1.2 millimolar. So the total is around 25, 24 plus 1.2. But remember, the total CO2 is always this plus this. It's always the bicarbonate plus the dissolved carbon dioxide concentration, both of which can change the total CO2. So again, just to reiterate what I said, the relationship between the total CO2 and bicarbonate, they are not the same thing. The total CO2 for practical purposes is equal to the bicarbonate concentration plus the dissolved carbon dioxide. And that we calculate by taking this solubility coefficient 0.03 times whatever our PCO2 is. So it's around a millimolar. Now, we can, in addition to getting the total CO2 from the metabolic panel, we can actually measure blood gases. So the question is, what are we doing when we measure blood gases? Well, we have a machine, and the machine has two types of electrodes in it. There's an electrode that measures the PCO2, or the partial pressure of carbon dioxide in the blood. And it also measures the pH, which is the negative log of the hydrogen ion concentration. It does not measure the bicarbonate. It doesn't measure the carbonic acid, and it doesn't measure the carbonate. So it's measuring two of the four substances again. And one of the four substances, the carbon dioxide, dissolved carbon dioxide concentration, and it's not measuring the other three. It's not measuring carbonic acid, bicarbonate, or the carbonate, but it is measuring the pH. So we can take advantage of that by looking at this equation, which is called the Henderson equation. You all remember the Henderson-Hasselbalch equation, which it has logs in it. And so what people did is, instead of having to use logs, they took the anti-log of the pK, the so-called pK in the reaction, and included in it the solubility coefficient of carbon dioxide to come up with this linear equation, which states that the hydrogen ion concentration equals 24. This is a constant. It's always true. It doesn't change in acid-base disorders. It's a constant number. 24 times whatever the PCO2 is over the bicarbonate. So this is what's measured by the PCO2 electrode. And the pH electrode, if you take the anti-log of it, you get the hydrogen ion concentration. But the bottom line is you're measuring these two things, and the blood gas machine calculates the bicarbonate from actually the full Henderson-Hasselbalch equation. It could use this too. So when you get the bicarbonate back from your blood gas machine, it's a calculated number. And some people erroneously think, well, it's calculated, so it's not accurate. And that's not true also. As long as the PCO2 and the hydrogen ion concentration assessed by the pH electrode are accurate, this has to be one number only. It can't be anything but what you get from this equation. So the bicarbonate is equal to 24 times the PCO2 divided by the hydrogen ion concentration. And the machine knows this. So you get three numbers, but remember, two of them are measured. Third is calculated. Now, the other reason for knowing the Henderson equation, again, the hydrogen ion concentration is 24 times the PCO2 over the bicarbonate, is because it represents organ physiology. The PCO2 is determined primarily by the lungs, and the kidneys determine the steady state bicarbonate concentration in the blood. So abnormalities in these numbers tells you medically or physiologically changes in organ function in the body. So it just doesn't have a quantitative importance. It has a physiologic medical importance. That's why it's really important to memorize this equation for that reason alone. And then, as I'll show, for checking the numbers that you get from the clinical lab. Now, the problem is, as you know, as you've seen already, is that the pH electrode measures the negative log of the hydrogen ion concentration and doesn't give you the H concentration, or to be chemically correct, it's actually the activity, not the concentration. But it doesn't give you this number. You have to either memorize this or ask ChatGPT to tell you what it is or calculate it. An easy way to remember is that a pH of 7 is a hydrogen ion concentration of 100, and this is nanomolar, 10 to the minus 9 molar. So much, it's a very small number when you think about it. And then you just take 80% of the previous number to get the remaining one. So 7.1 is 80, 7.2 is 64, 7.3 is 51, 7.4 is 40, 7.5 is 32. Notice we're just taking 80% of the previous number to get the next one. And you can interpolate in between. That's sort of a quick and dirty way of doing it on the floor. But if you just remember that pH of 7 is 100 nanomolar. Okay, pH of 6 would be 1,000 nanomolar, right? There's a log difference. Okay, pH of 8 is 10 nanomolar. Now, the other thing to realize, we have this equation, but the absolute value of these numbers differs in males and females. We tend to always think of these numbers, but these are male numbers. So 24 times a PCO2 of 40 divided by a bicarbonate of 24. The PCO2 of 40 and the bicarb of 24 you see in men. In women, the PCO2 tends to be a little bit lower, and the bicarbonate tends to be a little bit lower. So a bicarbonate of 25 in a female would be actually a little bit high. Don't go by the lab slips or the ranges you see clinically from the clinical lab, because their ranges are so sky high, you're going to miss acid-base disorders. I mean, if you look at your bicarbonate and you were doing the measurement and doing it every day, it's actually kept constant to the decimal point. Let's say it's 24.2 today, it would be 24.5 tomorrow, 23.9 the next day. It's kept within a very small range, almost to the decimal. It's just the clinical lab tends to, if you look at if the normal range is, I don't know what it says, 21 to 28 or something, that's just ludicrous when you look at large populations or again within a given individual. So remember the range at which you need to think of this is abnormal. Don't go by the lab slips. And that's true in medicine in general. The lab tends to give you ranges which exceed what you would typically see, at least in yourself, if you measured it from day to day. Or even if you compared individuals, they're way outside. Certainly true for acid-base numbers. The other thing you have to realize is that there are AV differences, and sometimes we get arterial blood gases, but as you know, sometimes we get venous blood gases. And for years and years, people have said on the wards, well, are venous blood gases just as good, or they're not as good? And the answer is they're just as good. They're not good for the PO2, but they're just as good for assessing acid-base disorders as long as you know what normality is. And that's true on the arterial side too. As long as you know what the normal starting value is in your patient, or compared to what it is in a group of patients, population mean numbers, then you can assess venous blood gases just as easily. Now remember that the pH is a little bit lower, the PCO2 is a little bit higher, and the bicarb is a little bit higher. And the reason for that is carbon dioxide is released from your cells from the Krebs cycle into the arterial blood that's coming to them to turn it into venous blood. So you just drive the bicarbonate buffer system from the left to the right here, where it's just like bubbling a solution with carbon dioxide or holding your breath. You raise the PCO2, and that drives the reaction here to create a proton and bicarbonate. That's where this bicarbonate's coming from. The pH is a little bit lower, and the PCO2 is higher because of the addition of carbon dioxide to the blood. So basically, we always have a respiratory acidosis on the venous side. You can think of it like that. Then when the blood gets back to the lungs, the carbon dioxide is excreted and the reaction is shifted to the right, or excuse me, from right to left. So the bicarbonate drops, the pH gets a little bit higher, and the PCO2 drops to what it is in arterial blood here. So basically, you have a bit of you have respiratory acidosis here. That's why the vein and the artery are different. Now, this difference in the PCO2 between the venous and arterial blood, which I showed here was above 3 millimeters of mercury, has been known for years and years to vary with the cardiac output. So as the cardiac output drops, the difference between the venous and arterial PCO2 increases. And people actually used to, in the 1950s and 60s, look at the AV PCO2 difference and to assess someone's cardiac output, because the cardiac output times this gap is a constant. So if you think of this number, let's say the cardiac output's 5, and this is around 3 or 4, this will be around 15. So this number is pretty constant. And so as this gap goes up, this number goes down. The numerator stays constant. And so it was sort of an indirect way of assessing the cardiac output. You just get a venous and arterial blood gas, look at the PCO2 difference. If it's like 7 or 8 or 9, someone's got a very low cardiac output. So it varies inversely. It's hyperbolic. Okay, so yeah, so the next time you get venous and arterial gases, or if you're worried on the ward about someone's cardiac output and you're not able to get, the cardiac output quickly enough, just get an arterial and venous gas. If the difference is 2 or 3, their cardiac output's fine. Okay, so let's look at the PCO2 first. And the PCO2 is determined by input-output considerations, just like everything else we measure. The CPK is determined by input-output considerations. Your bilirubin's determined by input-output considerations. Your potassium is the same as everything we measure. It's input versus output. And the same thing is true with the carbon dioxide. So we have, this level of 40 millimeters of mercury in a male. You can think of the thermostat being set at 40, but it's due to input and output being equal. So we have a carbon dioxide production from the mitochondria in our cells in the Krebs cycle. We're making 20 moles of carbon dioxide every day, and we have to get rid of it. So in the steady state, we have a PCO2 of 40. When we have a discrepancy between the input and output, that's when this number changes. If the excretion exceeds the input, it'll drop. If the excretion is less than the input, it'll go up. If our production goes up greater than our excretion, it'll go up, that sort of thing. We tend not to have production problems. Maybe when you have a fever or hyperthyroidism, the mitochondrial carbon dioxide production rate will go up, but as long as you're excreting that increased excess amount normally, you're not going to see a change in the PCO2. You only have changes in the PCO2 due to production problems if you also have an excretion problem simultaneously. So someone with COPD, for example, who's got chronic bronchitis, who then gets a fever or hyperthyroidism, their respiratory acidosis, acute respiratory acidosis above their chronic would be due potentially to increased production with the inability to handle that increased load. So instead of 20 moles a day, they might be producing 25 moles a day, and they can't get rid of the extra 5, so the PCO2 goes up. Remember, just so you have a rough idea, every day we're producing and excreting 20 moles a day. In a bottle of seltzer, we have 0.16 moles. So that just quantitatively gives you an idea of how much carbon dioxide we're actually producing. So the PCO2 in the numerator here is a function of what our lungs do, essentially. Now, the bicarbonate concentration is really a function of what the kidney does. The kidney and the body have a problem. If you think of the math here, in every liter of blood or plasma, there's 24 millimoles of bicarbonate, so the concentration is 24 millimolar. Assuming the GFR is about 140 liters a day, so we filter throughout all our nephrons about 140 liters of water a day. In each liter is 24 millimoles. That means we're filtering about 3.4 moles a day of bicarbonate. Huge amount. That's the amount of bicarbonate in a box of Arm & Hammer baking soda comes through all our glomeruli every day. And obviously, we're not excreting that in the urine. If you look at the urine of most humans, there's hardly any bicarbonate there at all. And that's because the nephron has absorbed it all after the filter. So there's like very, very small amounts of bicarbonate in the urine. 99% of this is being absorbed every day by the nephron, unless you have proximal RTA or other issues that prevent the bicarbonate from being reclaimed. If you had no bicarbonate reclamation or absorption after the filter, after the glomeruli, you'd be peeing out all your bicarbonate in about 4 hours, and your blood bicarbonate would be zero. So the kidney, this just gives you, a thought experiment to show you how essential it is, given all this bicarbonate coming through all our glomeruli, that we have normal nephron, normal transport processes that can absorb this bicarbonate back into our blood. So that's one thing the kidney has to do to keep the bicarbonate at 24 millimolar. There's a second thing the body is confronted with that would tend to lower the bicarbonate, that has nothing to do with bicarbonate reclamation by the nephron, but has to do with the fact that our diet produces protons. So every day on an average North American diet, we're produced it's actually the liver, which is the proton producing organ. The liver is pumping about 50 milliequivalents a day of protons into the IVC. And I'll show that that comes from some certain types of food. It's the anion is chloride or sulfate. So the liver is actually pumping into the IVC hydrochloric and sulfuric acid every day. The total proton load is about 50 milliequivalents a day. And that proton, when it gets into the um, hepatic vein, is going to react with bicarbonate to form. Basically, you're just driving the bicarbonate buffer reaction to the right, and you're forming carbon dioxide, losing bicarbonate, generating carbon dioxide. The carbon dioxide you just excrete. The lungs can handle that, assuming your medulla in your brain is sensing the carbon dioxide and your lungs are able to excrete it. The PCO2 won't change, but now you've got a lower bicarbonate concentration. It's no different than starting a hydrochloric acid IV yourself. So that you're normally doing this normally from your diet. Every day you're producing protons. And if you didn't have a way of regenerating that bicarbonate somehow, your bicarbonate just from the proton load would be zero in your blood in 2 weeks. It would be like starting an IV of hydrochloric acid at this rate and then just letting it run. If you do the math and look at the volume of distribution, et cetera, the bicarbonate concentration would reach zero in about 14 days or so. So clearly this doesn't occur. We're all sitting around with a bicarbonate of 24 millimolar approximately in our blood. So clearly some other process must be countering it, since most of us are generating protons from our diet. And it turns out when people look at the proton producing ability of food, it depends on the type of food. If you're eating cheese and egg yolks and meat and fish all day, you're producing a lot more protons than if you're eating raisins and spinach all day. So it depends on the type of food. Raisins and spinach and vegetables produce actually bicarbonate. It's the opposite issue, and the kidney just has to, dump the bicarbonate. But if you're eating meat, fish, eggs, cheese, et cetera, you're producing a lot of hydrochloric and sulfuric acid, and your kidney now has to do something. Now, I haven't said what it is yet, but the kidney has to counter that proton load somehow. If you're eating raisins and spinach and vegetables, you're generating bicarbonate, and all the kidney has to do is excrete the bicarbonate in the urine. So it turns out that to maintain this so-called whole body proton or proton bicarbonate balance, some people call it, there has to be something occurring that's going to counter this 50 milliequivalents of protons coming into the body every day. And it turns out the kidney actually generates an equal amount of what's called new bicarbonate to match the daily hepatic proton load. So you can think of it as two IVs. The liver is pumping hydrochloric and sulfuric acid, assuming you're eating meat and fish and cheese and that sort of thing, and eggs, around 50 milliequivalents of protons into the IVC every day. And the kidney is pumping 50 milliequivalents of new additional bicarbonate. Now, this is in addition to the bicarbonate that it absorbed from the glomerular filtrate. So you got to absorb the box of Arm & Hammer baking soda. But in addition to that, you've got to the kidney has to generate an additional 50 milliequivalents of new bicarbonate that didn't come in through the glomerular filtrate and pump that into the renal vein. And these two things match each other, and they create carbon dioxide when they meet, and the lungs just get rid of the carbon dioxide. So this is called whole body proton bicarbonate balance. And in end-stage renal disease or CKD4 and 5, the reason the bicarbonate concentration falls, the reason you get a metabolic acidosis is because the kidney slowly loses its ability to generate new bicarbonate. It has nothing to do with being able to absorb bicarb from the glomerular filtrate. There is, in some patients, some sort of renal tubular acidosis, which refers to an abnormality in bicarbonate reclamation. But in general, patients with ESRD who have a drop in their bicarbonate have so because they can't generate this new bicarbonate. The new bicarbonate actually is coming from glutamine. The carboxyl glutamine is converted to alpha-ketoglutarate, and alpha-ketoglutarate has two carboxyl groups on it that are neutralized in the Krebs cycle to make bicarbonate, or in gluconeogenesis also. But the carbon is coming from the carbon on glutamine predominantly, and people with CKD4 or 5 and ESRD, the kidney doesn't take up glutamine normally to turn it into new bicarbonate. So if someone says to you, why does my patient have a metabolic acidosis and they have ESRD, your answer should be one statement. My patient can't take up glutamine normally to generate new bicarbonate. Okay, so again, getting back to blood gases, the hydrogen ion concentration is not measured exactly. It's the pH, the negative log of that, and the PCO2 are being measured, not the bicarbonate, and the bicarbonate is calculated. Its concentration is calculated because these three things have a relationship with each other. You can use this equation called the Henderson equation, or you can use the full Henderson-Hasselbalch equation if you'd like. So now let's get to the clinical side of things. Now you're confronted with a bunch of numbers and your mind is overloaded. The question becomes one question only. At least there should be one question only in your mind, and that is, what should I look at to assess someone's acid-base status? Now, the default pathway is obvious, is always the pH in most residents and house staff. Please stop doing that. In fact, not only should this be called what I'm going to teach you, the bicarbonate-centric approach, but it should be called the non-pH looking at approach. Do not look at the pH, because if you use the pH to assess acid-base disorders, you're going to miss the exact diagnosis, and you'll definitely be missing mixed acid-base or complex acid-base disorders. So again, don't look at the pH, even though you'll see it all the time, and you're always tempted to look at it and say, okay, this patient has some sort of acidosis or acidemia because the pH is 7.32, but you're not going to be able to go far enough with that to know definitively what's going on chemically in the patient's blood. So what should you look at? Well, what you should look at is either the total CO2, which, as I mentioned, represents mostly bicarbonate. This you get from your metabolic panel. Or if the patient had a venous or arterial blood gas, you look at the calculated bicarbonate. Now remember, these bear a relationship with each other because the total CO2 is mostly bicarbonate. So it's going to be almost, it can never be lower than the bicarbonate. If the total CO2 on the metabolic panel is lower than the calculated bicarbonate, one of the numbers is wrong. Assuming they're both from the same type of blood, assuming they're both arterial or both venous. You can't compare mixed blood types of blood. But assuming they're both from the same types of blood, this always has to exceed this, and it usually is greater than the bicarbonate by around 1 millimolar. Okay, so if you want to know exactly how much it should be greater, you take the PCO2 of 28, multiply it by 0.03, and then add that to the bicarbonate, and that's what the total carbon dioxide content of blood is. So addressing the question, what should I now have the task of assessing the acid-base disorder in my patient. I willfully do not look at the pH. I look at the total CO2, or if I have it available, the bicarbonate. And I answer the question, is that value normal, increased, or decreased? So I'm looking at either the total CO2 or the bicarbonate, and I put it into one of three categories. Is the number normal, increased, or decreased? So clearly, you have to know what normal is. And that's why I say when you look at the lab slips, they have too big a range of normality. If in a male, you should accept 20, if the normal is 24, 23 would be the lowest you would accept as normal. Even that is getting a little bit abnormal in most males. 25 would be the upper normal. 26 already is too high. And in females, remember, 23 is the normal. So 22 to 24 would be the normal range. The PCO2 in a male, 40. Above 41, 42, you're already getting too high. And below 38, you're getting too low. So a lot of this isn't explicitly written in textbooks, but from these lectures and just from talking to people, you'll get a feel of what the normal is. But again, write it down and memorize it, because if you keep looking back at the lab slips, you're going to by default go into these categories that are way, way too big, and you're going to miss acid-base disorders, because part of the task here is, after willfully looking at the total CO2 or bicarbonate, your next question is to put it into one of these three categories, and you can't do this unless you know what the normal is. Okay, so if the total CO2 or two bicarbonate are below normal, then you have one of three acid-base disorders. It's either metabolic acidosis. So these are all the acid-base disorders, the three where the total CO2 or bicarbonate are decreased, or it's acute respiratory alkalosis or chronic respiratory alkalosis. So what you can also learn from this slide is it's not sufficient to just say metabolic acidosis, which most people would say. You also have to think, teaching point number two, you also have to think that it could be acute respiratory alkalosis, or could be respiratory alkalosis. And teaching point number three is that's not sufficient either, because we divide up respiratory alkalosis by temporal subdivision. It's either acute or chronic. It's not sufficient just to say the patient could have a low total CO2 or low bicarbonate from respiratory alkalosis. You have to say it could be acute or chronic. So that will give you the three. If you don't say acute or chronic, you're only going to have two choices. And certainly if you don't think of respiratory alkalosis altogether as a cause, you're only going to have the usual default metabolic acidosis answer. And you get wrong answers on your exams. And obviously clinically, you're not going to pick up everything. Now, the other thing to realize is in the acid-base disorders that lower the total CO2 or bicarbonate, the PCO2 also decreases. And we'll talk about what the implication of that is. So in these disorders, you have a decrease in both. They're both decreased. You don't have one normal, one going up. You don't have one up and one down. They're directionally in the same direction, both decreased in all three. And that, if you think of it, that becomes a problem. How am I going to distinguish these three? Then you might think, well, look at the pH. The pH will be low here and high here. But again, if you do that, you're defaulting to looking at the pH. And the whole point of this lecture and the whole lecture series is to stop looking at the pH to make an acid-base diagnosis. So we'll have to come up with a way then, without looking at the pH, to distinguish these three. So all three acid-base disorders have a decrease in these parameters. And so how do we distinguish them? And this is the clue here, or the key point. The key point is that the change in the bicarbonate, or the total CO2, from normal, when it's looked at in comparison to the change in the PCO2 from its normal, is what distinguishes these three. They all have a different proportion of change in bicarbonate to change in PCO2, which you must memorize. That's empirical. There's no way to predict that. They each have a different relationship of the change in bicarbonate from its normal level to the change in the PCO2. Now, I mentioned that the PCO2 is decreased in all three. So why would it be decreased in metabolic acidosis? Metabolic acidosis, we have either a loss of bicarbonate if we have a pancreatic or gallbladder fistula or renal tubular acidosis, or we have a proton load from lactic acidosis, or we have proton load in ketoacidosis. All these things drop the bicarbonate. Why is the PCO2 decreased? And the reason is when the bicarbonate drops in these disorders, our ventilation changes as an epiphenomenon. And we find that the ventilation increases. And that when the ventilation increases, it creates a discrepancy between the carbon dioxide production in the Krebs cycle versus the carbon dioxide that's excreted, and the PCO2 drops to some new level. We call that phenomenon respiratory compensation, or the compensatory response. And people have teleologically said, well, the body's trying to compensate for the change in pH, and that's why the PCO2 drops, and it's a way of bringing the pH higher than it would be otherwise had it not occurred. And that is true, but whether the body is doing it to keep the pH better than it would have been otherwise, there's literature to suggest that that is not true, and it shouldn't be called the compensatory response. We'll get into that in another lecture. So don't believe a priori, or don't believe with your entire mind that this is occurring because it's compensating for the pH, even though that's what you've been taught probably until now, because the literature suggests that that assumption is not true. And in fact, there are certain instances where the ventilatory response can actually make the pH even worse. And we'll show that another time. So, as I said, the goal here is not to look at the pH, but to come up with what the expected changes in these two parameters should be in each of the three disorders where the PCO2, where the bicarbonate and the PCO2 have decreased. So in metabolic acidosis, you have to just memorize this, and you can memorize the Winters formula if you like. For some reason, people like that. But if you just remember this change in both of these from normality, it's equally as good. So it's known that for every 10 decrease in the bicarbonate, your PCO2 should decrease by 12. So it's roughly 1.2 to 1. For every one decrease in the bicarbonate, the PCO2 decreases 1.2. You can do for every 5 change, PCO2 changes by 6. It doesn't matter. Bottom line is this is the proportion. If you see that, by definition, you have a compensated metabolic acidosis. It can't be anything else. It cannot be acute or chronic respiratory alkalosis. So, for example, if the bicarbonate is 14, which means it dropped by 10, the PCO2 should be 28, assuming it started at 40. So we're making some assumptions here that the bicarbonate started at 24 and the PCO2 started at 40. We don't know that with certitude. And if you don't know it, then you have to either assume population norms, which again in a male would be 24 and 40, or you have to know what this particular patient was when they didn't have an acid-base disorder. Maybe their starting bicarbonate was 23, in case this fell by 9. So you don't really know for sure the deltas. So it's an estimate always, unless you know that your particular patient was before this happened. Now, the other thing that we talk about in metabolic acidosis is the anion gap. And the anion gap is nothing other than something that falls under the concept of electroneutrality. And that is, in every solution, then positive charges must equal the negative charges. We don't, have a battery in our blood, or, we don't have a voltage across the aqueous solutions in our body. We have electroneutrality, which means that all the positive charges are going to equal to all the negative charges. So the anion gap is really a subset of this. So what are the positive charges? Sodium, potassium. We have 2 divalent cations, calcium, magnesium, IgG. Some of the proteins are charged, have a net charge. IgG is positively charged. That's why when you have myeloma and you have IgG chloride coming into your body, your anion gap drops, right? You have too many positive charges. So, and negative charges, but when we calculate the anion gap, the chloride is going up in myeloma, right? Because that chloride's coming in not with sodium, but with IgG. So mathematically, you'll see the anion gap goes down. And the negative charges are chloride, bicarbonate, phosphate. There's different forms, monovalent and divalent phosphate that have different charges, sulfate, and there's organic anions that are charged also. So if we just as a rule, which again is just a construct mathematically, you could have taken anything and subtracted it from anything. If you take the sodium and subtract from it the chloride and bicarbonate and call everything else unmeasured anions because you don't want to list them all, and all the other positively charged things, potassium, calcium, mag, IgG, unmeasured cations, you can see that you get this. So just conceptually, the anion gap can go up, or this difference on the left side can go up, either because the unmeasured anions went up, and the unmeasured anions, remember, include all of these things. Any one of them or combinations thereof, or the unmeasured cations went down. You were hypocalcemic and hypomagnesiemic and hypokalemic. That can raise your anion gap. Or your IgG level fell to nothing for some reason. That'll raise your anion gap. So again, this helps if you understand this, because there are things that can affect this difference that we're not measuring. And if you only think of these 3 things, you're going to miss things that could change the difference between them. Because the left side always has to equal the right side. And again, we're just saying that you have to have electroneutrality. Now, the other thing about the anion gap is that it doesn't cause the metabolic acidosis. People have this misconception that the anion gap is required or is the cause of why the pH either got more acidemic or why the bicarb fell, and it's not true at all. The anion gap is solely due in most clinical situations to the fact that we have excess anions coming into the bloodstream. The anions happen to come in with a proton. It's the proton which binds to bicarbonate and shifts the bicarbonate buffer reaction and lowers the bicarbonate to create the metabolic acidosis. The anion has nothing to do with creation of the metabolic acidosis. It's just coming in with the proton and the anion gap goes up. Okay, so when you have ketoacidosis, for instance, when you have acetoacetic acid or beta hydroxybutyric acid, the acetoacetate or the beta hydroxybutyrate raise the anion gap, but they're not causing the metabolic acidosis. It's the fact that they came in with a proton and not sodium or potassium. It's the same with lactic acidosis. The lactate is not causing the metabolic acidosis. It's coming with a proton. It's the proton doing it. If the lactate, when we got an MI or hypoperfused our tissues, came into the blood with sodium, then the anion gap would go up, but you would not develop a drop in your blood bicarbonate concentration. It's just that whenever you create these organic anions physiologically, they always come in with a proton. Now, it doesn't have to be exogenously. For instance, you can have carbenicillin, which is a sodium salt. People used to give that, to treat certain bacterial infections, and the anion gap will go up because of the carbenicillin anion, and that was not associated with a metabolic acidosis because you weren't giving the acid form of that salt. You were giving the sodium salt. And so the bicarb stayed the same, but the anion gap would go up. So you have to think of these two things as totally separate processes that are being caused by a substance coming into the blood, and each component of that substance does different things to each of these. So when we get a metabolic acidosis, we have to think, is it compensated or not? I mean, in other words, we're asking what is the PCO2, the ventilatory response, which is predictable. Again, for every 10 drop in the bicarbonate, your PCO2 should drop by 12. And what is the anion gap? Is the anion gap normally increased? Now, as I mentioned, the other two causes of a drop in the total CO2 or bicarbonate are either acute or chronic respiratory alkalosis. Well, first respiratory alkalosis, but I said it's not sufficient to say that. You always have to divide it up as to whether it's acute or chronic. And the reason the bicarbonate falls there is not because that was the initiating event. What happens in respiratory alkalosis is you drop the PCO2 as the initiating event, and the bicarbonate drops. Now we divide it up temporally because the magnitude of the bicarbonate drop for a fixed and given drop in the PCO2 differs. So if you have a drop in the PCO2 of, let's say, 10 millimeters of mercury, let's say in a woman it fell from 38 to 28, and I measure the bicarbonate, I'll get a drop in the bicarbonate initially within the first few minutes, but if I keep following that bicarbonate, it'll fall further. And that's why we divide it up temporally. For the same 10 millimeter of mercury drop in the PCO2, we're not changing this further. We're keeping it, we had a sudden step drop in it from 38 to 28, but this thing keeps decreasing with time. We'll show that in a minute. So we have a different name for the beginning and when it finally stops changing. Now that initial fall is solely due to the bicarbonate buffer system shifting the equilibrium. It has nothing to do with with an organ or the body. For instance, if I open a bottle of Coca-Cola, the PCO2, the carbon dioxide will leave, the PCO2 in the solution will drop, and I'll shift the bicarbonate buffer reaction from the right to the left. So as I drop the PCO2 in the solution, I consume bicarbonate. Bicarbonate with a proton will make carbonic acid, will make more carbon dioxide. So I'm shifting the equilibrium, and that's why the bicarbonate falls. Same thing occurs if you get anxious now during this lecture and start hyperventilating. Your PCO2 is going to drop, and the bicarbonate then will drop solely because you've shifted the bicarbonate buffer reaction to the left. It has nothing to do with the kidney. It has nothing to do with the lungs. It has nothing to do with any organ. It's just, it would occur if you took all your blood and had it bubbled. And initially, there was a top on here, and you open the top, you're going to see the bicarbonate fall. So that's what we call acute respiratory alkalosis. It's due to a shift in the bicarbonate buffer system. And it takes about 5-10 minutes for this to be complete. Very fast. So here's an example just shown diagrammatically, the difference between chronic respiratory alkalosis and acute. In chronic, the bicarbonate falls further than just from the bicarbonate buffer reaction shift. So here's a male with a PCO2 of 40. Let's say we drop the bicarbonate, or excuse me, we drop the PCO2 to some new level as a step change, let's say an instantaneous step change, which obviously doesn't occur clinically, but let's say it's very fast, and then keep it at some new lower level. And now we just measure bicarbonate every day in the blood or the total CO2 on the metabolic panel. And what you would see is the following. Initially, you would get this initial drop, which is small and fast. It's finished in a few minutes. And then bicarbonate would keep falling. And you'd have to wait a number of days until it stopped changing. And when you reach this sort of new steady state lower level, which is depicted by the blue arrow, we call that chronic respiratory alkalosis. Now, we don't have a name for everything in between here, even though we could. We just don't. We could call it subacute, subacute, but since it's a continuum, that would be too difficult clinically. We just have this initial event, which does not require an organ, just the bicarbonate buffer system shifting equilibrium versus the final level that we achieve that we call chronic respiratory alkalosis. Now, I haven't told you why it continues to fall. I'll just say in this lecture, it's due to the kidney. The mechanism we'll go over another day. But you need a kidney for this to occur. If you have a patient with ESRD and this happens, the bicarbonate's always going to look the same. It's going to stay only a little bit decreased, and it's always going to be decreased by the level that you would predict from the bicarbonate buffer reaction shift. You will not get this continuous fall. So you can be fooled, because if you have a patient who you know has been hyperventilating for a week, and yet the number, looks all the time like acute respiratory alkalosis. Yes, the blood chemistry is compatible with acute respiratory alkalosis, but clinically it's a chronic process because it's been occurring for a week. Let's say you took a patient with ESRD on a ventilator and you up the ventilator. It would always look acute. It would never look chronic. So you need normal kidney function for this to occur. Remember that. So then the question is, how do you distinguish the metabolic acidosis 10 for every 12 that I talked about from what occurs in acute or chronic respiratory alkalosis? And again, we just look at the delta bicarbonate and delta PCO2. And in acute respiratory alkalosis, for every 10 decrease in the PCO2, we get a 2 decrease in the bicarbonate. So it's a 5-to-1 relationship instead of a 1-to-1.2 relationship like compensated metabolic acidosis. Here, the bicarbonate change is 1/5 of the PCO2 change. In metabolic acidosis, they're about the same, 1-to-1.2 or 10-to-12. Roughly, the changes are pretty close to being equal. Here, you have a 5-to-1 difference. So this could never be compensated metabolic acidosis. And in chronic respiratory alkalosis, as I said, the bicarbonate falls further, so the total fall now is around 5. It fell 3 further than just the acute effect. So again, this could not be a metabolic acidosis compensated. The bicarb's down 5, the PCO2 is down 10. Yeah, they're both down, like in metabolic acidosis, it's compensated, but they're not equal. The PCO2 is twice as much as far as its change from normality than the bicarbonate. So when you see these kind of numbers, when there's a 2-to-1 difference and both are down, immediately this is a chronic respiratory alkalosis without doing anything more. And again, realize that with all these 3 things, we haven't looked at the pH at all. You don't need them. Just know what the relationship is between the change in the PCO2 versus the change in the bicarbonate for each of these. So again, in respiratory alkalosis, which has the same directional changes, the drop in the PCO2 and the drop in the bicarbonate, We have different phases, unlike metabolic acidosis. There's a temporal change in bicarbonate further as time goes on, which the kidney is doing. And so we have a name for this at the end, and we have a name for the beginning. We don't have a name for anything in between. And it takes a certain length of time for the bicarbonate to reach this new steady state level that we call chronic respiratory alkalosis. Now, what if the total CO2 or bicarbonates increased? Well, again, we have three choices. So if it's down, we have three choices. And if it's up, we have three choices. And you can memorize that. And that will cover all the acid-base disorders. 3 in the down direction, 3 in the up direction. Very easy to remember. If you're only coming up with one cause, you're a third of what it should be for that direction. So if the total CO2 or bicarbonate are elevated, and the only thing you can think of is a metabolic alkalosis, you've missed 2/3 of the possibilities. Because it could also be respiratory acidosis that we divide up into two temporally, either acute respiratory acidosis or chronic respiratory acidosis. But again, not only is the total CO2 or bicarbonate elevated, the PCO2 is also elevated. So both in the down direction of bicarbonate, you have the PCO2 down in all three, like we mentioned. And in the up direction, the PCO2 is also up in all directions. So we have an directional change, again, in the same direction for these three. Elevated bicarbonate, elevated PCO2. And now it's our task, without looking at the pH, to distinguish which of the three it is in our patient or in an exam. So what about metabolic alkalosis, the one everybody remembers first? If the bicarbonate's elevated, people don't realize this or forget it, but the PCO2 also increases. So it's the converse of what occurs in metabolic acidosis, where the bicarbonate decreased and the PCO2 decreases. If you increase the bicarbonate, either because you started vomiting or you had NG suction, or I gave you a ton of bicarbonate IV, or you developed Bartter syndrome or Gittleman syndrome or Little syndrome, or whatever the cause was, you will find that the PCO2 is also increased because you get a ventilatory compensatory response also in metabolic alkalosis. And people just seem to forget that. You don't just get the compensatory response in metabolic acidosis. You always have to remember that in the metabolic acid-base disorders, there's always a compensatory response, whether it's acidotic or alkalotic. The PCO2 changes also. So if you have any of these patients with a metabolic alkalosis, the PCO2 will not be normal, should not be normal. If it is normal, you have another acid-base disorder. Talk about that. So remember that the PCO2 also increases, and you have to make a diagnosis in your patient with metabolic alkalosis as to whether there's appropriate compensation or not, just like in metabolic acidosis. And then you have to know the expected change. So again, is it metabolic alkalosis is the question, and we look at the delta bicarb and delta PCO2. We do not look at the pH to see that it's alkaline. That's not how you do it. So the root, you have to memorize this, that for every 10 increase in the bicarbonate, the PCO2 goes up, not as much as in metabolic acidosis, where it's 10 to 12, but it's 10 to 7. So the PCO2 goes up, but not as much as the bicarb went up. It's around 70% or 7/10. So if you have a patient who started to vomit and the bicarb went from 24 to 34 and the PCO2 started at 40, you'd expect it to go to 47. If you see these numbers, 34 and 47, again, I'm not showing you the pH. Just looking at these numbers alone, this has to be a compensated metabolic alkalosis. Can't be anything else. Because the deltas were 10 to 7. So metabolic alkalosis, we don't divide by anion gap, we divide by whether giving chloride containing salts. And I say chloride because it's not the sodium that's important, it's the chloride you're giving that makes the bicarbonate return to normal. In some patients, in others, you can give as much chloride as you want and it won't correct, and we call that chloride non-responsive. But there are some patients who you can give chloride containing salts to, usually we give it as sodium chloride, and the bicarbonate returns to normal. And so we would like to be able to know who will respond to the chloride. And it turns out you don't have to give the chloride to figure that out. That's the beauty of the approach that people realize clinically. So how do we predict whether giving chloride or not will work or not? Well, the answer is you look at the urine chloride. And if the urine chloride is low, and by low, usually empirically it's less than 20 milliequivalents per liter, then you can pretty much predict that giving chloride IV, the bicarbonate will decrease to normal levels. However, if the urine chloride is normal, and by normal, the normal urine chloride is 70, 80, 90. It depends on your chloride intake and your how much water you drink. And obviously, the urine chloride in the chloride responsive group also depends on how much water they drink. If let's say it's 20 and they're drinking a liter, and now I tell the patient to drink 2 liters of water a day, the urine chloride will go to 10. So the chloride concentration is at the whim of your water intake, like all electrolytes. Whenever you look at the concentration of any electrolytes in the urine, it's a reflection also of your water intake, and you can make that number whatever you want, which is why it's better to look at 24-hour excretion rates, which have nothing to do with the water intake, or the fractional excretion, which again is a number which isn't determined by your water intake or water excretion rate, or the volume, if you want to think of it like that, that the ion finds itself in. It's independent of that when you do fractional excretion or absolute excretion. But when you do concentrations, remember, you can dial that number to be whatever you want just by changing the water intake. But be that as it may, these rules are reflective of a normal water and chloride intake. So if you see this and it's less than 20, then you can pretty much predict the patient's bicarbonate will be corrected. And if it's normal, you can give as much chloride as you want. You're wasting your time. Bicarbonate, nothing's going to happen to the bicarbonate. So we divide up metabolic alkalosis by its chloride sensitivity, whether it's chloride sensitive or resistant. So again, just to summarize, metabolic alkalosis, we determine if it's compensated, just like metabolic acidosis, in every patient. Don't miss any. And then you just don't look at the anion gap. You look at the urine chloride concentration to decide, is the patient going to respond to chloride? For acute or chronic respiratory acidosis, and I'll finish here, when the PCO2 goes up, the bicarbonate also goes up. That's why you have an elevation of both, not only in metabolic alkalosis, but in respiratory acidosis. All three have an elevated bicarbonate. It's just the bicarbonate elevation in the respiratory acidosis, whether it's acute or chronic, have a different mechanism. In these, it's the PCO2 which is causing it. So how does the PCO2 do it? Well, first, the PCO2 does it just from, again, shifting the bicarbonate buffer system equilibrium, just like in what I showed for acute respiratory alkalosis. This is just the converse. You're shifting it the other way. So it's no different than, let's say you have soda stream here and you bubble the water with carbon dioxide, you're going to generate bicarbonate in this solution. And so in your blood, if you raise the PCO2 by, let's say, stopping breathing for a few minutes or for a minute, your PCO2 is going to go up, but now you're shifting the equilibrium to the right and you're generating a proton and bicarbonate. So your bicarbonate is going to go up. Okay, and this confuses people. They think, well, aren't I making as many protons as I am bicarbonate? And that is true. You're making the same amount of each, but the protons don't go all free into solution. There are other buffers other than bicarbonate. There's albumin, phosphate, other proteins, and they bind most of the protons that are generated. So the amount that go free in solution that actually change your pH are very, very little. If there were no other buffers in the body and every proton that was generated went free into solution, you would die in a minute because your pH would be like 0. So the pH hardly changes because, yes, you make equal amounts of both, but these are bound to some things we call buffers, non-bicarbonate buffers. But all the bicarbonate goes free into solution. There's no buffer. There's nothing that binds this. So every bicarbonate made will change the bicarbonate concentration, but that's not true of protons. So that's something that confuses people. They think, oh, there's equal amounts of both. Why does anything happen? And the answer is these are all bound. The vast majority of these are bound. So this only changes by nanomolar concentrations, whereas this is changing in the millimolar range. Okay, so you stop breathing, your PCO2 goes up, you generate bicarbonate, has nothing to do with an organ, has nothing to do with anything other than the bicarbonate buffer system, and it's known how much that should change. But it doesn't stay constant. So let's say I had a PCO2 of 40, or I was on a ventilator and I stopped the ventilation. and my PCO2 goes to 50, 60, whatever it goes to as a step change, and I keep it there. If I follow the bicarbonate or the total CO2, yes, it will jump initially. That's just due to the bicarbonate buffer reaction, but it'll keep going up. And you reach a new steady state that we call chronic respiratory acidosis. So the bicarbonate differs for the same PCO2 depending on when we made our measurements on the patient. These are days here. And we don't have a name for anything in between, like I talked about for respiratory alkalosis. We just have a name for the beginning and the end, acute and chronic. So how do we distinguish whether it's metabolic alkalosis compensated or acute respiratory acidosis or chronic respiratory acidosis? Again, same thing. We don't look at the pH. We just look at the change in PCO2 versus change in bicarbonate. And it's known that for every increase in the PCO2, the bicarb goes up 1. So if the PCO2 went from 40 to 50, acutely, the bicarb would go from 24 to 25. PCO2 went from 40 to 60, the bicarbonate would go from 24 to 26. If it was a woman and the PCO2 went from 38 to 48, the bicarbonate would go from 23 to 24. So these are, you just have to memorize this. And this is certainly not anything like you see the 10 to 7 changes that you see in compensated metabolic alkalosis. Very different. What about chronic respiratory acidosis? Well, what happens is the bicarbonate keeps going up above that 1 change. So for every 10 increase here, this goes up 1, but the bicarbonate keeps going up. And so we have to have a new rule. And the new rule is that in chronic respiratory acidosis, for every 10 increase in the PCO2, if we come back through 4 days later or so, the bicarb has gone up another 2.5 from its original 1. PCO2 isn't any different. It's still gone up 10, but this has gone up 3.5. So you can see metabolic alkalosis, we have a 10 change in bicarb and a 7 change in the PCO2. Acute respiratory acidosis, we have a 10 change in the PCO2 and a 1 change in the bicarb. And in chronic respiratory acidosis, we have 10 and 3.5. So these ratios are very clearly different and allow you to distinguish which of the three in a patient who has an elevated bicarbonate. And I think we'll stop here just because of the time. What I'll do in the next lecture is go over clues that you have additional acid-base disorders present, and then we'll go through a number of cases where you can practice your skills in making the acid-base diagnosis. And those cases are also interesting, and they have additional subtleties that I think you'll find interesting. So thank you, everybody, for joining, and we'll see you next time.